So our title today, as you see, is Empirical Bayes Methods, Theory, and Application. I think Jiaying gave an amazing overview of a lot of the theory in the first half and kind of the tools available in this area. So I'm just a kind of humble, lowly labor economist, an applied person. So I'm here to do the application part. My goal is to sort of show you how these tools play out when applied in a couple of concrete examples. And hopefully in doing that, communicate that this is not only a set of tools, but kind of a way of thinking about empirical problems that I think has broad applicability to a lot of the types of settings that economists are now after in practice these days. So just to motivate that point a little bit, as Jim said, maybe because of the rise of large administrative data sets, large-scale social experiments, maybe just the forward march of science, economists in a lot of different literatures these days are increasingly doing what you might call drilling down to study heterogeneity in fine-grained, unit-specific parameters. To be more specific, in my field of labor economics, a few examples, a classic question in labor is the return to education, so the causal effect of additional schooling on your labor market outcomes, your earnings. The traditional way of thinking about that question is about the effect of going to school for an extra year. But as that literature has progressed and become sort of refined, we've now started to think about returns to particular types of education, returns to, say, going to a more versus less selective college, as in famous work by Dale and Kruger. More recently, returns to specific individual colleges, as in work by Mountjoy and Hickman. Example 2, another classic question is about industry wage premia. So do some industries pay more for the same workers, maybe because of efficiency wage considerations or rent sharing or compensating differentials, other types of reasons? The modern incarnation of that type of idea is a large recent literature using matched employer-employee data to look at premia associated with working for specific individual firms and what the distribution of those firms, firm effects looks like. Final example, it's long been of interest in labor economics and public economics. What's the effect of the neighborhood that you grow up in on your future outcomes? Is it good for a kid's, say, future earnings to grow up in a neighborhood with a low poverty rate versus a high poverty rate? In recent influential work in this area, Raj Chetty, Nathan Hendren, and co-authors have done a series of papers trying to drill down and look not just at low versus high poverty, but effects of specific neighborhoods, counties, or even finer geographies like census tracts. What's the effect of one census tract versus another? And I think in all of those types of settings where we have these estimates of many unit-specific parameters, effects of individual educational institutions, effects of individual firms, effects of individual neighborhoods, empirical Bayes methods provide a very useful framework for thinking about answering those sorts of questions on several dimensions. Okay, so first we could ask questions about the distribution of parameters across units. How much better are the best neighborhoods than the worst neighborhoods? What's the spread in neighborhood quality look like? That's a question about a distribution of parameters. Empirical Bayes has a natural way to approach that. Second, once we know something about that, we can also use this to improve our estimates for individual units. Rather than thinking about each neighborhood or school in isolation, we can kind of interpret the estimate for each individual unit in the context of coming from a distribution of many estimates that we know something about. And we can derive estimators and decision rules for each individual unit that, in some aggregate sense, as Jiaying said, perform better than estimates that consider them in isolation. And finally, for making decisions. So this includes both policy-type decisions. If I have some policy that I want to select a specific set of units, maybe I want to recommend to people what neighborhood they should move to, maybe I want to select schools as high or low performers, Empirical Bayes gives us a way to think about what functions of the data should we use to make those sorts of recommendations. And then second, more practically for us as scientists, this can help us with decisions about what to report. If I'm doing a study of firm effects, I have estimates of 1 million firm effects. It's probably not a great idea to make table 1 of my paper just a printout of 1 million estimates. Okay, I want to distill that information, produce some kind of function of that information to communicate to the audience what's going on in this context. I think the EB philosophy is a really useful way of trying to digest that information and decide what to report. All right, so with that as background, the goal for my part of the talk, I'm going to recap some very basic theoretical elements that Jiaying already covered through 2 concrete applications and see how they play out. The first is an application to school value added in Boston, estimating the effectiveness of middle schools. This is loosely based on the Angrist et al. 2017 paper on the reading list. There I'll take what you might call a classic parametric EB approach just to see how the methods work and get comfortable with using them. Second application will be application to a large-scale resume correspondence experiment trying to study the distribution of discrimination across large employers in the US labor market from a recent Klein-Rose-Walters paper. There we'll extend the classic parametric approach to try to leverage some recent tools in non-parametric and robust EB and see what kind of extra stuff we can get using those tools. So I don't have photos of my co-authors, but it goes without saying that the other names on this slide contributed a lot to this work, and I'm largely learned much of this from them. Okay, so let's get into the first application just to set the stage. I can go quickly through this because it's similar to some things Jiaying already talked about. Let's think concretely about a population of students in some district, say Boston, that we're interested in studying. Index the students by I. Each student is going to attend one of capital J schools in the district. And I have in mind a very simple potential outcomes model where every student I has a potential outcome, yi of j, associated with attending each of the possible schools in the district. So yi of j tells me how I would do at j in terms of an outcome. Think of a test score. Okay? I'm going to take a very simple model for those potential outcomes, an additively separable model with a school effect beta j and a student effect epsilon I. Okay? So beta j, we're going to call that the value added of school j. It's a causal parameter giving me the quality of that school. Epsilon I is everything else, represents unobserved student heterogeneity, family background, ability, whatever. I'm going to normalize the mean of that to 0, so you could think of the betas as mean potential outcomes. This is a simple model because it's all constant effects. If I take any student and move them from, say, school K to school J, in this model, the effect of that is beta J minus beta K. So no heterogeneity, no match effects. We could obviously add those, but for our purposes, it's going to be simplest to keep things in terms of constant effects to learn the tools. All right, so even in that simple model, there's several questions you could be interested in this setting. First, you might be interested in the value added of a specific school, say beta 1. How good is the school that's in my neighborhood? Maybe I want to know the answer to that. Second, I might be interested in features of the distribution of the betas across the schools. How much does school quality vary? Are all the schools in this district kind of the same, or are some much better than others? That's kind of a distributional question. And third, I might be interested in making a decision that depends on the betas. Maybe I have to decide which school should my child attend. I have some option of which of these schools to go to. Maybe I'm a district policymaker. I have to decide which schools to select for some kind of expansion or closure policy. That's a question where I might have an eye on the value added of those schools when making that decision. And as we'll see, EB methods are going to be useful for helping us answer each of these types of questions. Although the first one, there's some subtleties there, and we'll get into that when we get there. All right. So how to operationalize this? Let's move towards what we get to see in the data. Of course, that's a potential outcomes model I just laid out. For each student, I get to see the potential outcome associated with their actual treatment choice, which is yi. I've written that here as just a sum of school attendance dummies, d, times the value added parameters, plus the student heterogeneity term. In this literature, we're usually worried about selection bias. We don't think that students are unconditionally randomly assigned to schools. There's a lot of sorting. So a first cut at trying to fix that, we can control for some stuff. And typically, a key control is last year's test score. So try to control for lagged achievement. Hope that soaks up a lot of the selection. Let's call that vector of covariance x. It's got last year's score, maybe some other demographics in there. Project the student heterogeneity term epsilon onto x. Residual from that projection is u, so that's uncorrelated with x by definition. I've substituted that in to my equation here. Maybe I should use this little hand to show you what I'm talking about. And then let's suppose everything works perfectly as we'd hope, and that additive control for x is enough to kill all the selection bias in this environment. The component of potential outcomes that's left over after I do that, the u, is uncorrelated with the school attendance dummies, so everything's great. And this causal equation, remember the betas are causal parameters, coincides with the population OLS regression of y on d and x, so I can get those coefficients from OLS. All right, that's great. I go into a sample of data. I run my value-added model, as we call this, trying to estimate the value added of the schools. At the end of the day, what I get from that is a list of beta hats, one for each school, value-added estimates, along with their standard errors, and we'll call those SJ. All right, so that's the starting point. We have a beta hat J for each school, an SJ for each school, a collection of those for the capital J schools. And now we want to think about what to do with that. All right, and for a lot of what we do, I'm going to make this assumption here, which is, again, along the lines of what we saw in the first half for a lot of the discussion. I'm going to assume that beta hat is approximately normally distributed, centered at the true beta for that school, with a sampling variance that's well described by its squared standard error. So I'm thinking of this as a kind of loose asymptotic approximation. Center limit theorem is kicked in. My estimates are normally distributed. They're kind of centered in the right place. I know something about their sampling variance. They kind of behave like a normal. I believe my standard errors. We can talk later about what happens when my samples get small enough in each cell where maybe that's not a good approximation, but for now, let's work with that and see what happens. All right, all that's pretty standard. All I've done so far is run some OLS regressions. Now is where things get interesting. Okay, so we move to the second level of the hierarchy, and we think about a distribution of those betas across the schools in the population that we're studying. I'm going to call that distribution, following the same language Jiaying was using, G. Okay, so I'm going to think of the betas as random. They're draws from a distribution G, each a draw from that same distribution. That's my mixing distribution, and that plays a key conceptual role in the EB framework. Okay, why is it a mixing distribution? Well, for each individual school, what I see is a beta hat with normal noise, and then the means of each of those draws are drawn from a second level distribution, so I'm seeing like a mixture of normals, and that's my mixing distribution. It's important to emphasize that in this framework, G is not like a subjective prior. Okay, this looks sort of like a Bayesian thing, but G is an objective feature of the world in the way I'm thinking about this. It, in particular, answers concrete questions about how value added works in this district. What about that first question I asked? How does school quality vary? How much variance is there? G answers that. That's the variance of G, would be a sensible answer I could give to that question. Another way of thinking about it, how much better are the best schools than the worst schools? Maybe 75th versus 25th percentile of value added is the right answer to that question. That's G inverse of 0.75 minus 0.25, okay, difference in quantiles of that distribution. And so the next step, if I want to answer questions of that type, is the EB deconvolution step, okay, where I'm going to use my noisy estimates along with what I know about their sampling variances, the SJ squareds, to deconvolve the beta hats and extract an estimate G hat of the mixing distribution G that I can then use to answer these types of distributional questions about what's going on across all the units in this population. All right, that sounds good, but I think it's worth stopping here a little bit to dwell on the philosophy of G. So if you're kind of a very practical program evaluation sort of oriented economist, you might think I've tried to slip something past you with that assumption. You might say, what does it mean to say that the value added parameters are random draws from a distribution? Okay, at the end of the day, maybe I should take a fixed effects perspective. There's capital J schools in this district. They have value addeds. Those are the betas. Each school has one, but those are just unknown numbers. They're out there in the world. So what's this G thing that you're talking about? Why do I need some kind of distribution involved in this? This looks like some harmful econometrics or something, some Bayesian or random effects kind of stuff. All right, so one unsatisfying answer I could give to that is that maybe I should think of the observed schools as sampled from some larger superpopulation of schools that could have existed but don't exist. And G is the distribution of value added in that superpopulation. There might be some applications where that makes sense. I think for a lot of applications that's going to be an unsatisfying defense of this type of assumption. Where are the missing hypothetical schools in Boston that could have existed but don't exist, and why would I want that to influence my view on what type of econometrics I should use? So I'm going to kind of reject that way of thinking. Instead, I think we can motivate this random effects perspective in a more instrumental type of way by the objectives that we have as econometric analysts. In particular, even with a finite population of schools, in a pure kind of fixed effects perspective, I can ask how the beta J's are distributed across that finite population. I can sort of do a thought experiment where I say, what would happen if I kind of sampled from the finite population of betas? What distribution is induced by that thought experiment? there is an answer to that question, and I can learn something about that from my data, because I have an estimate of a bunch of the betas. And because of all of the elegant theorems and so forth that Jiaying laid out, it turns out that if our loss function cares about average performance across schools, we want to do something that involves all of the schools, okay, make a decision, report an estimate, it's valuable to incorporate that distributional information into our estimates for individuals. Okay, and so the G is sort of an instrumental way to get us towards a tractable framework for doing that. As you'll see in a second, we often in practice use continuous or IID models for G. I'm going to write down like G is a normal distribution or something. In the pure fixed effects kind of finite population view of the world, that strictly speaking can't totally make sense. There's only capital J possible mass points in that distribution, but I want you to think of that as sort of a parsimonious approximation to whatever's going on. One lesson you could take away from the discussion today is I don't actually have to get everything about G right necessarily for the estimators and decision rules that come out motivated by this perspective to perform well even in purely frequentist type terms. Okay, so you could think of this as an approximation, and then we're going to go forward with that. One last note on this philosophy slide. One thing this discussion is not about is about whether the betas are correlated with the x's that I stuck in my value-added model. So I think it's kind of an unfortunate quirk of econometric terminology that we often use random effects to refer to a kind of panel data estimation strategy that imposes an independence restriction between the betas and the distributions of the x's in that regression, whereas fixed effects, we're not doing that. So you might kind of remember back to graduate school, something about that. Random effects means independence, fixed effects means I don't assume that. That's actually kind of a separate question. You know, whether I want to view the betas as fixed or random is a different question than whether I want to view them as independent of something else that varies in the population of schools. So you could think of this as kind of a correlated random effects approach. I haven't taken any stand on whether the x's are related to the betas. In fact, I probably think that they are. That's why I wanted to control for x in the first place. But I still want to view the betas as draws from a distribution. All right? So that's my philosophy of G. Hopefully you'll give that to me and we can move forward. Everybody's still on board. And let's do a parametric version of this. Okay, so let's suppose G is a normal distribution independent of the sampling error Sj. What does that mean? Okay, we'll come back to that, but let's just impose that for now. Then we have this very simple hierarchical type model where for every school J, I have a beta hat J. Conditional on the beta for that school and its standard error, I just have a normal distribution centered at the truth with variance Sj squared. And then at the higher level of the hierarchy, the betas are drawn from a normal distribution that doesn't depend on the standard error. It's the same distribution for schools with different standard errors. It just has two parameters, mu beta and sigma beta squared. We call those hyperparameters because they kind of live at the top level of the hierarchy. They're parameters of a distribution of parameters, so they're hyperparameters. And under this normality assumption, to do deconvolution, all I have to do at the end of the day is estimate those two parameters, because once I know those two things, I know everything there is to know about G. All right, so how would I go about estimating those? There's a variety of ways, which again, Jiaying already touched on. A very simple way you could think about estimating these, I'm trying to estimate the mean of the betas. Well, I'll just take the mean of the beta hats. Okay, that's gonna work, that's fine. To estimate the variance of the betas, what I would typically do is compute this quantity right here or something along these lines. This first part is the sample variance of the beta hats. Okay, look in my data, look at the beta hats. How much did the beta hats vary? And then I'm going to subtract off the average squared standard error from that. Okay, why am I doing that? Well, you could think of that as a bias correction, okay, that fixes the fact that because of the noise in the beta hats are necessarily going to be over dispersed in my sample, even if all the betas were the same. So there's no dispersion in value added in the district. I'm going to get some chance variation across the beta hats that I get to see. How much will my standard errors tell me about that? And I can take that out. I subtract off the average squared standard error. If I get a positive number for sigma hat beta squared in this expression, that's what we call over dispersion, meaning the beta hats are more dispersed in my sample than what I would expect from the sampling error alone. Okay, so the SJs sort of tell me how much dispersion should you expect. If I see a much wider spread in my value-added estimates, they're over-dispersed. I've got over-dispersion. I'm going to infer a big random effects variance of G from that phenomenon. Of course, there's other ways to do this estimation procedure. I could have done maximum likelihood on the model I just wrote down. As we'll talk about later, the variance estimator I wrote down here is not actually exactly unbiased, but it's going to be consistent as J gets big. Klein, Saggio, Solvston have a kind of general framework for unbiased estimation of variance components. We're going to apply that in the second half, but for now, let's stick with this simple kind of method of moments looking type approach. All right, so that's my deconvolution, and actually in this simple normal model, once I've estimated those two hyperparameters, I can answer all the distributional questions that we started with. I know how much value added varies, I know the difference in any two quantiles, because there's only really two parameters of that distribution. Now what can I say about the individual schools? Okay, well, a natural thing to do, as we've been discussing, is to take that normal model and compute my posterior mean for each individual school's beta, given all the information that I have. In particular, I know that school's beta is a draw from G, and then I get another signal of the beta, it's the beta hat, I know its variance, and I just do a normal updating problem on that, and that leads to this simple linear shrinkage formula right here. Shrinkage because I'm pulling the beta hat towards the grand mean of G in proportion to the signal to noise ratio. So if I have a huge standard error on beta hat, I'm not really going to trust the beta hat very much. I'm going to shrink that a lot. If there's a lot of variance, sigma beta squared is big in the population, I'm not going to do as much shrinkage because I should expect there to be a lot of dispersion in the betas. All right, so this is the posterior mean in the normal case, but like many things in life derived from normality, it has some attractive robustness properties. In particular, I can also think of this as the fitted value from a linear regression of the latent beta on beta hat in a regression that lives in the population of schools. And that sort of inherits all the usual minimum mean squared error linear approximation type properties that we're used to with linear regression. So this is kind of an attractive thing to do with linear shrinkage. I could think that might be a useful quantity to compute, even if I'm not totally sure that G is a normal distribution. All right. As written, I can't actually implement that formula that I just wrote down because it has unknown parameters in it. I don't know the sigma beta, I don't know the mu, but of course I just showed you how to estimate those. So the empirical Bayes philosophy is to just stick a hat on those unknown parameters of G in my posterior formula and compute an EB posterior. So that puts the E in EB. It's now an empirical posterior EB beta hat J star. So I put the hat on the beta to indicate that I've now used my G hat estimate to form the posterior mean. So at the end of the day, what I've done, if I implement this, is to shrink the estimate for school J using the hyperparameters that I estimated with the larger pool of schools in my sample. I have many schools. I use that to learn something about the distribution, and then I use that distributional information to compute a posterior for each individual school. It works out very simply in this linear shrinkage example, but that's actually a much kind of broader idea in empirical Bayes. The empirical Bayes philosophy is to use a deconvolution estimate G hat as prior when I form whatever posterior quantity is of interest to me about individual schools. Okay? This has various names in the literature. Efron and Morris 83 call this borrowing strength from the ensemble. So I've used the ensemble of estimates across all the schools in the district to refine my estimate for each individual school J. Efron, 2012, in his book, calls this learning from the experience of others. In some sense, I have data on many different units that kind of have a shared experience. They're in the sense that they're in some way or other scientifically relevant in the same way that individual J is. So I learn from the experience of those others how to interpret my estimate for any individual school, and I use that to form my plug-in empirical Bayes posterior. All right, so that's the three-step empirical Bayes recipe that we follow in many examples. Step one, you estimate some effects in some way or other. We did OLS, but of course you could do all kinds of different things. I get a beta hat at the end of the day and a standard error on that. Step two, I do a deconvolution. I use the beta hats and what I know about the noise in the beta hats to extract an estimate of the mixing distribution G. I get my G hat, and then I have step three, posterior formation. I treat that G hat as my prior, and I update with beta hat and along with its standard error to form a posterior. Here, in this case, it was the posterior mean, but I could think about other quantities, and we'll talk about that in a second. All right, let me pause right here to ask if there's any questions about the cookbook that we've developed so far. All right, no questions. We can keep going. So let's kind of switch back a little bit to philosophy here. This is the cookbook empirical implementation, but when would I actually want to do this? So should I prefer the shrunk posterior mean to the unbiased estimate beta hat that I started with? And the answer is that it's actually not obvious. It depends on my goals as a researcher. So one way to see that is to say, let's say treat the value additive school J, the beta J, as a fixed parameter, condition on that, and compute MSE for two estimators, the unbiased estimate beta hat and the posterior mean beta star, for the moment abstracting from the fact that I'm going to do EB rather than full B. That's actually not going to affect the conclusions of what I'm about to say. So the mean squared error of my unbiased estimate is, of course, just coming from the variance. It's SJ squared. When I do shrinkage to form the posterior mean, I've introduced some bias. So I've got a variance term and a bias term in here. The variance has gone down because I shrank it towards a constant, so I'm removing some of the sampling variance. But of course, my bias has gone up. And if for some schools, it may have gone up a lot, actually, if I treat those as fixed parameters. In particular, if I'm only interested in one school, beta 1, and I don't care at all about the other schools, it's not at all obvious that by doing this shrinkage, I made things better for school 1. In fact, if that school is atypical, so it's very far from the mean, it's different than the other schools in the ensemble that I have estimates for, I've introduced a lot of bias, and I could easily do worse on mean squared error grounds by doing shrinkage than by not doing shrinkage. Okay, so shrinkage always reduces my variance, but it might introduce substantial bias if the school is very different from average. I think this point is even clearer if you think about a case where you have a collection of estimates that came from totally different contexts. So, maybe I'm a labor economist, I'm sitting in my office, I have an estimate of the returns to schooling, I'm excited about that. My macro and IO colleagues walk into my office and tell me estimates of their favorite parameters, like the inflation rate or the elasticity of demand for frosted flakes or something like that, whatever they happen to be studying. Should I take those estimates and shrink my estimate of the return to schooling towards the mean of those other two parameters? That would be kind of a crazy thing to do. Why would that be crazy? It's because I don't care about those other parameters for the purposes of my analysis, and I'm not guaranteed to get a better estimate of the elasticity of labor supply by shrinking it towards this other stuff. Okay, so if I'm only interested in one thing, not obvious I should do this. Okay, but in a lot of these contexts that we talked about on the first slide, we're actually interested not in one thing, but in many things. In the ensemble of estimates that we have. Suppose in the value-added case, we're interested in all the schools. We have some kind of compound decision that we're thinking about making, and my loss function is averaging over the schools in this population. It's not just about one school. In that case, the relevant notion of MSE is going to integrate over the mixing distribution G. Rather than treating beta J as a fixed parameter, I'm going to integrate that against G. That doesn't change MSE for the unbiased estimate beta hat. I still get SJ squared. But if I work that out for the shrinkage formula, beta J star, my MSE becomes this, which is just the shrinkage factor times SJ squared, which is strictly smaller. Why does that work? Well, it can't be the case that all the schools in the district are atypical for the district. Okay? In some sense, the average school must be average. The typical school must be typical, and so the biases across the different schools sort of average out, and I'm guaranteed in an aggregate sense to do better across the ensemble and get lower mean squared error. Okay, so the linear shrinkage estimator is superior if I want an estimator that on mean squared error grounds performs well on average across all the schools that I'm studying. And I've done this calculation in the simple normal case, but this actually holds, as Jiaying said, much more generally. It holds whether or not G is normal. I don't even have to adopt a random effects sort of view of the world for shrinkage to dominate the maximum likelihood estimator on mean squared error grounds in the compound decision problem. So if I wanted to do that, but I'm not sure that G is normal, I could also do a kind of robust inference procedure that acknowledges that uncertainty along the lines of the Armstrong et al. Paper, as Jiaying mentioned. All right, so let's implement this for the value-added example now that we're comfortable with the tools. Here's my deconvolution step. Okay, I've taken a list of beta hats and their standard errors for different value-added models. Over here, I have an uncontrolled model, which doesn't control for anything. We think that's badly contaminated by selection bias. The middle, I have a lagged score model where I've controlled for lagged y, and then here I have a gains model where I've kind of differenced relative to lagged y rather than controlled, kind of fixed effects type intuition, differencing out unobserved heterogeneity, you can see there's massive so this is my sigma beta hat estimate. It's my estimate of the over-dispersion in the beta hats, how much signal variance is there in the underlying G distribution. Okay, and you can see that there's massive over-dispersion in the uncontrolled model. That's, of course, mostly selection bias, but there's still over-dispersion in the lag score and gains models. I get a sigma beta hat somewhere on the order of 0.2 student test score standard deviation. So moving up one standard dev in the distribution of school quality, I expect my students' test scores to go up by something like 0.2 sigma. On the right-hand side, I've done this within sector, so taking out sector effects, by which I mean different types of schools, charter schools, pilot schools, and traditional Boston public schools. And you can see that brings down the within sector variance a little bit. We'll talk about that again in a second. All right, so that's my deconvolution step. I've now learned something about the distribution of value added in this district. The schools are very different. Some schools are better than others. Okay, what about my posterior means? Here's the histogram of value added estimates for Boston. In blue, I have estimates for traditional BPS schools. Those are like the schools within the district. I've also put separately the histogram for Boston's charter schools. There's a large body of literature studying charter schools in Boston, suggesting they're high value added relative to the district, so it's useful to break them out in this way. You can see the standard deviation of the unadjusted estimates, the beta hats, is 0.22. That's going to be too big. My deconvolution estimate of the standard dev of the prior is 0.197, so that means there's actually a lot of signal in the beta hats. It's mostly signal, not that much noise. If you take the ratio of those two numbers and square it, that says about 80% of the variance in the beta hats is actually true school quality variation and not sampling error. And if I'm working with this simple normal model, my prior distribution looks like this. It's just a normal distribution centered at the mean with that deconvolved sigma beta hat variance. All right, and then what about my posterior means? Well, I just shrink towards the mean in proportion to the signal to noise ratio. Those are, so that's the solid bars here. You can see that by construction, those are less dispersed than either the noisy beta hats or the prior distribution. So I'm shrinking them down. They're always going to have less variance than either of those two other quantities. And I sort of pulled in the tails of the distribution towards zero. There's some shrinkage going on, but again, because there's a lot of signal here, not everybody's getting shrunk down to the mean. There's still a lot of information about the quality of individual schools in these data. One thing you may have noticed about that picture is that the charter histogram looked a lot different than the traditional public school histogram. The charters are all kind of over here. On the right-hand side, the publics are further to the left. You might think I should incorporate that type of information into my empirical Bayes procedure, and indeed we often want to do this. So taking the kind of F-round phrasing, we could call this learning from the experience of which others. Maybe I think there's some other characteristics that I get to see in my data that are in some sense relevant. Schools that share those characteristics are more similar, have more similar experiences than schools that don't share those characteristics, and I want to build that in to my procedure. In a parametric model, a very simple way to do that is just to write down a conditional model for G. Simplest version is just to say I have a vector of characteristics C. Maybe it's got a dummy for charter status in it. Maybe it has some other stuff. And say I'm building a conditional prior, where the mean of that now depends on a linear index involving C. Here I've made it homoscedastic, so the same residual variance around that doesn't depend on C. I could obviously relax that too if I wanted to. And then to estimate that, I would follow the same type of procedure we did before. I could estimate this coefficient mu by just regressing the beta hats on C. I can deconvolve the residuals from that projection to get an estimate of the sigma R, and I form my EB posterior mean. It's just going to shrink me towards a linear index, a linear fit from that procedure rather than a constant, but otherwise everything works the same. So here's what happens when I do that. This is a prior distribution with a charter school location shift imposing common variance. You can see it's shifted to the right. The estimate of the charter effect is something like 0.3 sigma in this case. So this does two things. One, it gives me a richer prior that has these two location points depending on the school's covariates. Second, those covariates absorb some of the residual variation in school quality my residual standard deviation is only about 0.14 instead of 0.19, that means I'm going to be able to do more shrinkage because I've built stuff into the model that actually explains a lot of the variance of school quality. I'm going to get a more refined posterior out of that. So here's what I get when I do that. You can see if you kind of compare this to the previous picture, I'm doing more shrinkage than I was before. The other interesting thing you can see, this actually goes back to Jesse's question in the break, is I'm treating the charter schools and the non-charter schools differently, actually, in these two procedures. In the unconditional shrinkage procedure, I had this set of charter schools that had estimates kind of near zero, a little bit below zero. The unconditional prior thinks that those are basically typical schools. Shrinking them towards the mean essentially does nothing, so they remain in the same location. When I do that, if I build charter status into my prior, what I'm doing is shrinking towards the sector mean, and actually those schools get moved up above the average because this prior thinks they're more likely to be close to the charter mean than the overall mean, and I shrink them in that direction. You could think, depending on what your covariates mean, that may or may not be a desirable thing to do. Maybe you have some horizontal equity concerns or something that influence your view on what should be built into the prior. If all you care about is mean squared error, of course, this is what you should do. All right, a couple of extensions before we move to the second application. First, one kind of extension that's often coming up increasingly in empirical practice is a case where we have multiple estimates, actually not just one, of the same parameter, and some of those are better than others in the sense of coming from more credible research designs. Okay, so in the Boston Public Schools context, this is very natural. We have some OLS estimates like I just showed you, which are just controlling for some stuff and hoping for the best. And then we also have some lottery estimates that came from randomized admissions lotteries where we really believe the research design, we think we have partial random assignment, and we can get a good estimate of school quality out of that. So to show you how this might work, let me change notation. Instead of calling OLS beta hat, I'm going to demote it and call it alpha hat. Okay, so it's just an estimate for each school J, alpha hat. And I'm no longer sure that that's an unbiased estimate that selection on observables holds. Instead, I'm going to say that alpha hat is centered at something, which is the true beta plus maybe a bias component BJ that could vary across schools. So maybe OLS is overrating some schools, underrating other schools. I have the standard error on the OLS. As before, I'm going to, again, treat that as the normal distribution centered at that point, but that might not be the right point anymore. And let's suppose I have another estimate that's asymptotically unbiased, call that beta hat. Maybe that's an IV estimate that I got out of a randomized lottery. Why asymptotically unbiased? Well, again, this is why this normality thing is an asymptotic approximation. We know IV is never unbiased in finite samples, but I'm hoping that my asymptotics have kind of kicked in and I can treat my IV estimate as centered at the truth. It also has its own standard error. I expect that to be actually much bigger than the OLS standard error in general. OLS is precise, but maybe it's biased. IV is unbiased, but maybe it's imprecise. So one kind of traditional thing I could do here is just a Hausman test, compare OLS to IV. Are they giving me the same answer? Probably not. Maybe my Hausman test rejects. So should I just throw away the OLS and report the IV? That's something I could do. In the empirical Bayes view of the world, it's actually quite natural to retain both and think about forming my best estimate of the quality of an individual school, given all the available information, including the biased OLS and the unbiased lottery estimate. Okay, so I would use the ensemble of both OLS and IV estimates to estimate a joint distribution of truth and bias. I can kind of get a handle on that by saying how similar are the OLS and IV estimates? What's kind of the distribution of the difference between those two things? What does that look like? Is it correlated with the truth? I could be more or less flexible with that. And then I form my posterior, which you might call a hybrid posterior beta hat star, which in this normal model is going to end up just being a linear combination of everything I get to see. It's putting some weight on the lottery estimate, some weight on the OLS estimate, maybe corrected for some mean bias, and then weight on the prior mean. And the weight I assign to OLS is going to depend on the relative precision of the two, of course, and also how biased it is. So if I conclude that OLS is not biased at all, probably that's all I want to use. If it's a little bit biased, I put more weight on the lotteries and so forth. So in the paper, I'll refer you to the paper for other examples of this. There we generalize this to the under-identified case where actually all that's identified is certain linear combinations of value added, not the beta hats themselves, but you can kind of get a similar type of hybrid estimation procedure out of that. This work by Chetty and Hendren is trying to do something similar with neighborhoods where you have estimates based on permanent residence, and also some more quasi-experimental research design based on people that move between neighborhoods. All right, so here's just a picture from the 2017 paper on improvements that you get out of this hybrid strategy. You can see a couple of things going on here. One is that, especially for the very badly biased OLS, you get huge improvements from using the lotteries. That's coming both from the fact that you have a lottery estimate now to use, and second, the distribution of lottery estimates tells you how much to trust OLS, and it turns out that, especially in this uncontrolled estimate, you shouldn't really trust it. You should put very little weight on it. That brings down the bias a lot. You can also see that the hybrid estimates that involve the quasi-experimental variations, the lottery variation, tend to have higher variance than the biased OLS. That's kind of natural. That's the bias variance trade-off that's being solved by this hybrid posterior. All right. Last thing on schools. So we've learned a lot now about empirical Bayes posterior means. This approach delivers estimates with low MSE. So if MSE is your objective, the posterior mean is your go-to. Okay, but we often have other goals besides minimizing MSE. Maybe we have other policy objectives, other kind of things that we're trying to do. Jiaying also alluded to this. A very simple toy example of that in the school value-added context is, suppose I'm interested in a policy that's trying to select schools in the lower tail of performance. So instead of just reporting a good estimate of value added for every school, I'm trying to find the schools that are not doing so well. Formalize that by trying to find schools that are below some value added cutoff C. Maybe that's a quantile of my estimated G distribution, maybe it's some fixed number that I just started with. Let me write down a loss function that sort of formalizes that objective. This is a very simple type 1, type 2 error loss. So my loss function for a decision delta, which is a dummy 0 or 1, along with the truth, the beta, is delta times indicator for beta is bigger than C. So that's an error where I labeled a school low performing, but it's actually good. Plus 1 minus delta times beta less than C. Okay, so that's an error where a school is actually not so good, but I failed to label it as such. And then there's a cost kappa associated with that, a cost 1 associated with this error. Okay, cost 1 of mistakenly selecting high-performing schools, cost kappa of failing to select low-performing schools. What should I do? Well, if I care about this equally across all the J schools in the district, I write down my risk function, add it up over the schools, integrate this over the distribution of the data and the prior. You can probably immediately see that the right answer to that question is to, instead of selecting on the posterior mean, select schools that have sufficiently high posterior probability of being below the cutoff C. Okay, and how sure I want to be before I label that school as low performing depends on my relative cost of type 1 or type 2 error. How worried am I about accidentally labeling, failing to label a low performer versus accidentally selecting a high performer? So this is in general the decision rule. If you invert that CDF in that expression, what this tells me is that I should be using posterior quantiles to make this type of decision instead of posterior means. In other words, I should select schools by the posterior 1 over 1 plus kappa quantile instead of the posterior mean. In the normal case, the decision rule looks like this right here. And you can see that this is going to treat two schools that have the same posterior mean differently, depending on which one has a noisier estimate. This first piece right here, that's the posterior mean. That's the linear shrinkage part. And then I have this part here that says multiply by a function of the standard error, this inverse normal transform. Okay, and that depends on my relative costs of each type of mistake. And that thing is going to cross 0 at 1/2. Okay, so if I was equally worried about the two, actually I should select on the posterior mean. If I'm more worried about type 1 versus type 2, I should do something else and either reward or punish schools based on their standard errors. Okay, conditional on their posterior means in this case. And so, of course, as before, my EB decision rule is going to plug in the estimated hyperparameters into that expression, put a hat on the mu and on the sigma, and I could do that in my data. All right, the lesson here is different objectives call for using different functionals of the posterior for decision making. So instead of just reporting the posterior mean all the time, maybe we should think about exactly what we're trying to do. Maybe MSE is not the right goal in our particular context. In that case, maybe we want to think about a different functional of the posterior. Gu and Conker in their 2021 paper go into much more detail on these kind of EB tail selection problems. This is just a very simple toy example of that. All right, so that's it for schools. I'm going to take a kind of digression now before we move into the second application and try to connect some of the methods we've learned so far to other commonly used methods in the recent applied econometrics literature. So we sort of motivated the analysis here by this idea that we have many estimates for many units, a lot of beta hats, okay, many betas, they're noisy, the beta hats are noisy. I want to do something about the noise to fix that and get a better estimator. And you might say, that actually sounds a lot like this thing I've heard about machine learning. Okay, I thought machine learning was supposed to deal with problems where I have a ton of different parameters I'm trying to estimate and kind of fix the noise problem in that sense. There's a reason that those two things sound similar. They are similar, and in fact, in some cases, depending on how you look at the problem, they're the same thing. So I think it's worth demonstrating that in a particular very simple example. All right, so let me make my model even simpler. Instead of this value-added thing, instead of worrying about controls and different sample sizes and so forth, let's just suppose we have a really simple normal means model, n students per school. All I'm trying to do is estimate the mean for each school. I have homoscedastic normal noise, mean 0 at every school, and then my prior mean is also going to be 0, so the betas are just drawn from a normal 0 sigma squared. In that case, of course, my unbiased estimator is just the mean, y bar. My variance of that is sigma squared over n, and my posterior distribution, since everything is normal, is also going to be normal. It has the now familiar shrinkage formula for the posterior mean, and then this variance right here, common across the schools because everybody has the same sample size, the same standard error. But let's suppose I didn't actually know what beta j star was yet, and let's think about what the posterior distribution of the betas looks like in that problem. Okay, in general, my posterior density for beta j, given the data for that school and the prior, is just the likelihood of the, by Bayes' rule, is just the likelihood of the data times the marginal for the prior over the integrated version of all that stuff. Okay, I already cheated a little bit. I told you I know the posterior distribution is going to end up being normal. So in a normal distribution, the mean and the mode coincide. And therefore, I can also think of my posterior means as the maximizers of the posterior density. Okay, so I'm going to write the posterior means, the beta j stars, the things we've been talking about, instead of as E of beta given y bar and so forth. I'm going to write that as the argmax of the density in this kind of log likelihood formulation here, which if I plug in the normals is just going to look like this. I've got a log of the likelihood of the data given the parameter plus log likelihood of coming from the prior plus constant that doesn't depend on anything I care about. In general, we call this kind of estimate the maximizer of the posterior density, the map estimate, maximum a posteriori. In this case, it's the same as the posterior mean because it's normal. But let's write down what that looks like. Okay, let's use that formula for the posterior mean beta star. Because I'm using normals, log of a normal density, I'm just going to get a bunch of squares in there. Okay, I've got squares, squared deviations coming from the likelihood of the data. I've got squares of the prior coming from the prior. Let me multiply through by the scale factor on this first thing, -1 over 2 sigma epsilon to get rid of that. That turns the max to a min because I multiplied by a minus. And so what I've got here is a sum of squared residuals for the data, okay, plus a constant, which is this variance ratio, times the sum of squared betas. And my beta stars are the minimizers of that expression right there. So that kind of looks like something. This is a regression, okay, where I'm taking a sum of squared residuals plus a constant times what you might call a penalty term, which is quadratic in the betas. It's just the sum of squared betas. So that's called something. What is that? Somebody tell me. Quiz. Ridge regression. That's ridge regression. This is just regularized least squares with an L2 penalty, P, which is kind of one of the simpler, basic so-called machine learning algorithms that you may have heard of. So ridge regression is EB with normal priors. Why EB? Well, turning this from Bayes to empirical Bayes, I would be choosing the tuning parameter in this penalty function. You can see that the tuning parameter that I kind of want to use in this Bayesian framework is this variance ratio that essentially depends on the signal to noise ratio in my estimates. Right? This thing is n times my standard error. This thing is the variance of the prior. Those are the same hyperparameter type things I was trying to estimate before. All right, so I can think of empirical Bayes as kind of empirically choosing my tuning parameter, doing this regularized least squares thing, ridge regression instead of normal EB. So the punchline of that is that these sorts of regularization ML procedures often have an EB type interpretation. I could think of ridge as posterior means from a normal model. If I wanted L1 penalization instead of L2, so I want an absolute value in my penalty term instead of a square, so I want to do lasso instead of ridge, I could have gotten that by just making the prior here have an absolute value in place of the square. That would be Laplace distribution instead of a normal. Remember, the Laplace density just replaces the square with an absolute value. So I can think of lasso as computing maps, maximum a posteriori, from a model with double exponential Laplace priors on the betas. That's all fine. I guess the takeaway is when doing model selection or penalization via ML, it's sometimes useful to think in this empirical Bayes type of way and think about what implicit prior distribution you may have imposed on the parameters and also the connection to your loss function. So here you've sort of baked in what functional of the posterior you're going to report. That may or may not be the right idea depending on what type of decision you're trying to make, as we just learned with the mean squared error versus selection rule type loss. So I think this is a useful kind of connection. There's a lot more on this in this paper by Abadi and Casey if you're interested in reading about that. All right, any questions about any of that before I move to the final application? Okay, so application 2, now that we're all familiar with empirical Bayes, we sort of know the philosophy, we know how the tools work, we're now going to use some of the more recent like flexible EB type tools that Jiaying taught us in the first half in a second application. This is going to come from our paper Klein, Rose, Walters forthcoming that applies these types of methods to try to study the distribution of labor market discrimination across large employers in the United States. In particular, the structure of the experiment underlying this paper is a large resume correspondence study. Okay, so we sent fake resumes to a bunch of real job openings, and we did that in a kind of hierarchical structured way. So we selected 108 giant companies from the Fortune 500. Each of those companies, we tried to sample up to 125 jobs, each job in a different US county, so spread across the whole country. For each of the 125 sample jobs for each employer, we sent 8 applications, stratified 4 black applicants, 4 white applicants. How do we convey race? We're following the sort of literature here. You might be familiar with this Bertrand and Mullainathan paper, which manipulates employer perceptions of race using race and sex distinctive names on the resumes. We did the same thing. So we signed 4 distinctively black names, 4 distinctively white names at each job, applied to those jobs, 125 jobs per firm, 108 firms in the experiment. All right, so that has this kind of natural hierarchical structure, which makes it a good test bed for these EB-style methods. All right, let me develop some notation like we did before for thinking about what we're going to get to see out of this experiment. Let's start with potential outcomes. There's a lot of hierarchy here, so a bunch of subscripts. Let's call y I, j, f of r, which is a dummy variable, a potential callback to applicant I at job j nested within firm f if that applicant is assigned race r, which is either a b or a w. And then I can use that to define the average treatment effect at this particular job and firm, which is just the average difference in the white versus black potential outcomes at that job. You might notice I've imposed a kind of SUVA assumption here already by writing these as functions of only your own race assignment. You might be worried about that since there's maybe screening going on where all these applications are getting read at the same time. For what we do next, that actually doesn't matter because we're going to aggregate everything up and treat the jobs as observations. But the notation is a lot more complicated to show you that, so you can just think of this simple potential outcomes model to motivate what we're going to do. Of course, what I get to see, again, is the observed, the potential outcome associated with the realized treatment assignment, which is either a distinctively black name or a distinctively white name. And at the job level, what I can compute is just the treatment control difference, the mean difference in callback rates for white versus black applicants. I'm going to call that treatment control difference delta hat JF at that job for that firm. That's a very noisy estimate. Of course, I only have 4 treated and 4 control observations in that particular cell of the data, but I randomly assigned race, so it's an unbiased estimate of the average treatment effect. It's just super noisy. All right, so that's what's going on at the job level. Now let's aggregate up to the firm, which is going to be the level of interest in this experiment. Let's call delta F with no J subscript the average of those job-specific treatment effects, the delta JFs, across all jobs in that firm. So I'm abusing notation a little bit by putting a sub F on this expectation, but hopefully you know what I mean. Think only about firm F, average across all the jobs I could have sampled for that firm. Think about averaging the job level treatment effects, and delta F is that firm level average. Okay, so what I get to compute for that firm is the average of the jobs that I sampled, the average treatment control difference across those jobs. I'm going to call that delta hat F. I randomly sampled these jobs for each firm. So random sampling of the jobs plus random assignment of the treatment means that this thing at the end of the day is going to be an unbiased estimate of the firm level average treatment effect, the delta F. And I'm going to use this simple standard error estimator, SF squared, which is just the familiar standard error. It's an unbiased estimate of the sampling variance of this mean. Okay, and that's my step one of my EB cookbook. Okay, that's my effect estimation. At the end of the day, I've collapsed all the data for this giant experiment down to 2 numbers for each of the 108 companies, a treatment control difference and a standard error on that. And those are my building blocks. I'm now going to move on to step 2. Okay, remember step 2 of EB is the deconvolution step. I'm thinking about my G distribution. I'm going to call G the distribution of contact gaps. That's my label for the delta Fs across firms in the population. So there's 108 of these firms. There's some distribution of the treatment effect of a distinctively white name across those firms, and G is telling me about that distribution. It answers questions that I might be interested in about the concentration of discrimination. For example, if I see a difference in callback rates for white versus black applicants, is that difference driven by a small number of firms that intensively discriminate in a population of otherwise unbiased companies, or is everybody discriminating a little bit? Okay, so that G distribution answers questions like that. Anything I want to know about the distribution, that's a question about G. I would like to estimate that. I'm going to start by estimating its mean and variance non-parametrically the way I did before, but then instead of just assuming everything is normal and I only need those 2 parameters, I'm going to apply some of these more flexible deconvolution techniques to try to get a little bit more information about what's going on in the G distribution. Here are the means. Okay, the mean is easy to estimate. I just take the sample mean of the estimates. In the end, in this experiment, we got a 23% callback rate for applicants with black names, 25% callback rate for applicants with white names. So the average treatment control difference, average white-black callback difference across all the firms in the experiment is around 2 percentage points. That is a standard error of 0.002, so T statistic over 10, highly statistically significant. I'm also going to show you gender. That's over here on the right. This is male versus female. That turns out on average to be an extremely precisely estimated 0. Minus 0.001 is the point estimate with a standard error of 0.003. Okay, so those are the means. What about the variance of G? I'm going to do something that looks very similar to the simple estimator I used before with a couple of embellishments. Okay, so here's my sigma hat delta squared, my estimator for the variance of the contact gaps across the firms in the distribution G. This looks a lot like what I had before. Okay, here's my sample variance of the delta hats. I've done the usual degrees of freedom here. I'm dividing by F minus 1 on that. I'm subtracting off the average squared standard error from that, and then I'm sticking another degrees of freedom correction F minus 1 over F out here in front of that. Why do I want to write it that way? Well, it turns out that that particular estimator is a special case of the unbiased leave-out variance component estimator of Klein-Saggio-Solvston, which gives me an exactly finite sample unbiased estimate of sigma squared, even in a finite population where I'm not promising to get infinite firms, even in the finite population of F firms. Here I can think of this as an unbiased estimate of the quadratic form that I need to form the variance. Okay, why does that work? Well, one intuition for that is if I plug in delta bar, I plug in that formula for the standard errors that I showed you before, I can rewrite the variance estimator like this. Turns out to be just a function of a bunch of cross products of job-specific estimates across jobs at the same firm. So essentially what I've done is take all the possible cross products that I could construct for any 2 random jobs sampled at this particular firm. I'm treating those as independent. Okay, so those are basically firm effect plus uncorrelated noise. So each of those is essentially an unbiased estimate of delta F squared. And then I've got many, many different ways to do that. In fact, I've got JF choose 2 of those at every firm, so I'm averaging over all of those, and I'm averaging over all the firms, and then here's my other component of a covariance. So I could think of this unbiased variance component estimator as essentially an average covariance that gives me the right answer for the variance in this population, works in finite samples. All right, so what do I get when I do that? Here I'm showing you the bias-corrected standard deviation of the contact gap. So I took the unbiased variance estimate and I square rooted that. what I get for race is a number around 0.019, around 2 percentage points, so the mean and the variance are comparable. You could think of that as a lot of heterogeneity. There's as much spread, one standard deviation move up in this distribution that's comparable to the mean white-black difference in the experiment. For gender, interestingly, the standard deviation is even bigger than that. It's 2.7 percentage points. Maybe that's surprising because the mean is exactly 0. So how could that be? The mean is 0, but there's a huge variance. That must mean there's discrimination going on in both directions. Actually, there's some firms that are discriminating against men, some firms discriminating against women. I think this is one way of illustrating the power of these EB-type methods. If I just ran my experiment, took treatment minus control, called it a day, I would have said there's no gender discrimination. That turns out to be way wrong. Many of these firms are discriminating on the basis of gender. They're just doing it in different ways, in different directions. And that'll come out even more clearly in the deconvolution that I'm about to do. Okay, so that's mean and variance. Now let me move on and talk about learning more about G beyond the mean and variance. So I'm going to think about this hierarchical structure. Okay, I have a delta hat for every firm. I'm going to now call that normally distributed. I didn't need that for the thing I did in the last slide, but now I'm going to say I have enough observations at each firm to get a normally distributed delta F. Its standard error describes its sampling variance, and then I want to know about this G distribution, which is the marginal distribution of the deltas from the population that I drew from. An important note at this point, which we also learned from Jiaying, is that in doing this, if I want to be very flexible in how I do it, I need to account for possible dependence between the effect sizes, the delta Fs, and the standard errors, the sampling variance, the SF squared. So somehow from line 1 to line 2 in this picture, I got rid of the SF. I'm no longer conditioning on that. I'm thinking of the marginal for delta. How did I do that? Well, I have to do something to either integrate out SF or assume it's independent or something along those lines. That's actually kind of substantively interesting. So how would such dependence arise? There's a couple of different ways. What's the delta hat? The delta hat is a treatment control difference. So, my usual OLS standard error is sigma squared, variance of the outcome, over n times variance of the treatment. Variance of the treatment is the same for everybody because it's an experiment assigned 50-50. So any standard error heterogeneity that's going on here is coming from sigma squared, variance of the outcome. That's going to be driven by the overall callback rate at the firm. In particular, firms that never call you back actually have a standard error close to 0, okay? Because that's p times 1 minus p for a binary outcome. Firms that call you back around 50% of the time have a maximized variance. And you might think actually that the level of discrimination is related to how often they call you back in general. If a firm never calls you back, they can't really discriminate in levels. So there's a natural reason to think I might have this kind of heteroscedasticity and dependence built in. Another way that could happen is through the n that's in the denominator of my standard error. We tried to get rid of that by sampling the same number of jobs and so forth in this experiment, so we're not as worried about that. In this case, in other applications, you might be worried about that if there's n heterogeneity, like in the teacher value added example that we talked about earlier. All right, so how do we deal with that? Well, let's sidestep it in step 1 of the deconvolution, and we'll come back to that. Let me sidestep the variance dependence issue by transforming everything into a z-score. Okay, let's call ZF the z-score for firm F. It's just delta hat divided by S. Okay, just scale everything by its standard error. And let's call mu the population counterpart of that. Okay, so it's the real delta, the latent delta measured without error divided by S for each firm. I can write my hierarchical model in that world as Z is distributed with mean mu and variance 1. Since I've z-scored it, I got rid of the variance heterogeneity. And then the mu's themselves, the population z-scores, have some distribution in the population of firms. Okay? And that deconvolution problem is a bit easier. I don't have to worry about the variance heterogeneity. I can apply some of these tools to that immediately. I'm going to start with the Efron 2016 exponential approximation that Jiaying taught us, which basically approximates this G mu thing with a distribution in a smooth but flexible exponential family. In particular, we parameterize the density with a flexible spline. We estimate the parameters of that by penalized maximum likelihood. And you can actually do this yourself if you ever face this type of problem, automated in this nice deconvolve R package, described in this paper right here. This does require you to choose a tuning parameter to decide how much to penalize when you're doing penalized MLE. I think a nice way to do that, which is what I'm going to do, oops, in the next slide when I show you this is to calibrate that penalty term to match something else that you're pretty confident about that distribution. For example, we're going to calibrate the penalty so that the g hat we get out of this has the same estimated variance as that unbiased variance estimate that I just showed you, that I got from the KSS, Klein-Saggio-Solfsten type procedure. That's one thing I could do. The other thing I could do is the NPMLE, which we also learned a lot about. Okay, that picks the mixing distribution to maximize the likelihood of the observed data. As we learned, the solution to that is a discrete distribution that has at most F mass points. That's a known fact about this problem. If you're an applied economist like me, you may kind of remember this from graduate school from Heckman and Singer and be vaguely disturbed because this is notoriously difficult to compute. But fortunately, that's improved a lot in recent years. As Jiaying told us, Conacher and Mazera developed this approach to computing this problem, which is a lot easier than the EM algorithm type things that we used to do. So you can do this easily. You can do it yourself off the shelf with the RE Bayes R package now, as described in this Conacher and Gu article. Comparing these two types of estimators is a very interesting thing. When does one perform well? When does the other perform well? I won't go into that, but we learned something about that in the first half as well. And this Conacher paper is a nice little like meditation on which circumstances these different flexible deconvolution approaches perform well in. All right, so suppose I did one of those two things. I have my g hat mu. Okay, I have an estimate of the population distribution of z-scores. And now what I care about is the effect sizes themselves, the deltas, not the mu's. I need to do something to go back to levels from z-scores. In other words, I need a change of variables. So my delta that I care about is actually mu times s, right? It's the z-score times the standard error. And I have to do something to deal with that. Simplest thing I could do, which might be a good approximation, we'll come back to talk about this in 2 slides, is just assume independence of mu and s. Suppose the population z-score is independent of the sampling variance. Okay, that could be true. If we have dependence in levels, actually maybe we don't have dependence in z-scores. That could happen. We can test that. Let's just suppose that's true. If that's true, then I can just compute the distribution of the deltas through a simple change of variables formula that looks like this. And then I put a hat on everything. I have an estimate g hat mu from either Efron or NPMLE. I stick that in here. I integrate over the distribution of the standard errors. We're going to do that by just averaging over the EDF, empirical distribution function of the standard errors, and get an estimate of the mixing distribution. Okay? So here's the histogram of the white-black contact gap estimates across the firms in this experiment that we're summarizing. That's the histogram. You can already see it has a kind of interesting shape, right? It's sort of, it's kind of high near 0, but there's not very much mass at all to the left of 0, and then it sticks out to the right. And that's going to emerge in the mixing distribution estimate also. So here's the basic Efron estimate. That actually doesn't do a great job of matching the mean, which remember was 2.1 when I forced it to match the variance. But something interesting, a constraint you might want to impose on this is to notice that there's very little mass actually below 0 in that distribution. In the paper, we do formal tests of that. You can actually use some techniques from the moment inequalities literature to ask, are all the deltas weakly positive? So can I reject that every firm in this experiment weakly favors white applicants? It turns out you can't reject that. The p-value on that is 1. Okay, so the data actually really like that. And if you want to impose that, you get a little bit more kind of precision on the mixing distribution, and it looks like this. Turns out to look kind of like a log normal. Okay, so we've got some mass here near 0, but a longer tail of discriminators that are discriminating a lot against black applicants. Now I'm doing a very good job of matching at both the mean and the variance that we showed you before. So this is imposing that shape restriction that all the support of that doesn't extend to the left of 0. Here's the NPMLE. If I do that, again, this is going to be a discrete distribution. So it's spiky, but I think the substantive conclusion is kind of the same. We're getting, it wants to put weight that's pretty far out here in the tail. So it's saying there's some firms out there in the population that are discriminating 5 percentage points, more than twice the mean effect in the experiment, or even more than that. All right, so there's kind of a tail of discriminators that are favoring whites by a large margin. What about gender? Remember, for the first 2 moments, which we estimated before, things look quite different. The mean is 0, and then we have a huge spread. You can see that in the histogram. Things look different. It's symmetric about 0, but then we have some firms sitting out here way in the tails. If I do my Efron smooth deconvolution, it looks like this. It looks more like a Laplace distribution that's very peaked at 0, but then it's got kind of fat tails in both directions. NPMLE agrees. It wants to put mass way out here in the tails, both against men and against women. So this mixing distribution estimate is saying there's some firms out there that are going in both directions quite a bit, actually. And that's something that I couldn't have learned just from the means. That highlights, I think, the value of some of these methods. Okay, something interesting you can do with that, if you do these flexible non-parametric type deconvolution methods, rather than assuming normality, is compute other functionals of the distribution that are kind of interesting. What we've done here is to compute the Lorenz curves for discrimination implied by those Efron 2016 G hat estimates. So we might be familiar with Lorenz curves from the public finance literature looking at concentration of income distributions. You can do that for any random variable. Here we're doing it for the delta Fs, the discrimination. For gender, I'm actually doing this for the absolute value of delta F because it goes in both directions. So I'm kind of saying what is the concentration of the total gaps against either men or women look like. And you can see that this is a pretty concentrated distribution. One metric for that is how much of the total discrimination in the experiment is driven by the top 20%, firms in the top quintile of discriminators. That's about 50%, a little below 50% for race, over 50% for gender. All right? So let's return briefly to this precision dependence issue. What I assumed to get those distributions out of my z-score distribution estimates was to assume independence of the population mu's and the standard error is F. If that's true, that actually imposes the assumption that the effect sizes themselves, the deltas, are proportional to the standard errors. If I kind of do this simple calculation here, it says delta is equal to mu bar times S. If I do E of delta given S, you might think that's a reasonable approximation, actually, because as we said, if nobody calls you back, they have a very small standard error and probably a small contact gap. If they call you back more, they have a bigger standard error, maybe they have a bigger contact gap. I can kind of test that assumption, actually. We look at that in the paper. It seems to fit reasonably well. There's other types of more flexible things you could do. So you could treat SF as a covariate that shifts the location or the scale of G in the same way that we did with the kind of charter school indicator in the earlier parametric analysis. You could do a VST, a variance stabilizing transform, try to find a function T, basically, such that the variance of the transformed contact gap, delta hat, conditional on delta, but not the standard error, is variance stabilized. There's known VSTs that work for certain data generating processes. You could use the data to try to find something that works well here if you wanted to. Another thing you could try to do is estimate the bivariate distribution, actually, of both. So you could say I have a marginal for delta, I have a marginal for F, I have some joint between those, and I could actually try to estimate that from the data. That's asking a lot of the data, but you could do that, for example, with NPMLE and impose less restrictions on the way this heteroskedasticity interacts with the effect sizes. All right. The very first kind of poor man's approach to that is to just split your sample by sampling variability. So here I've just taken the above and below median firms in terms of their precision of their delta hats, estimated my deconvolution separately for both. You can see this kind of works the way that I'd hope, given that assumption on the z-scores. The firms with low standard errors, they all have pretty small contact gaps because they're basically not calling anybody back. Okay, so they have a very compressed distribution. The higher standard error firms also have a wider distribution. In that sense, the approximation that we used seems to fit pretty well. You could also form the marginal from this kind of split for the full distribution of the deltas. It looks like this. It's a little bit lumpier because it's combining these two distributions, but for key functionals like the mean or the standard deviation or the top 20% share, which we showed in the paper, it actually turns out to perform basically the same. All right, last step. So I've done my first two steps of my EB cookbook. I did my effect estimation. I've done my deconvolution. What about step 3, firm level posteriors? Okay, well, I have my estimate of G hat in hand. Let me move on to step 3. I can form my EB posterior mean. Okay, one way to do that here is to take the z-score posterior mean from the G hat mu and just multiply that by S to get my posterior mean for delta, which I'm calling delta F star. I can compare, as we did before, the distributions of the unadjusted contact gaps, the mixing distribution, and then the firm level posteriors. I already showed you this picture. Here's the empirical Bayes posterior means layered on top of that. Again, as always, by construction, those are less dispersed than either the unbiased noisy estimates or the mixing distribution itself, but there's still some dispersion there that tells me that this experiment contains a fair bit of information about the individual firms. All right, kind of last topic I wanted to get to, I guess I have around 15 minutes left. And I want to leave some time for questions, so I'm going to go through this very quickly. Sort of parallels what we did with schools. You know, all of this is about minimizing MSE so far. If I want a good estimate that minimizes MSE for each of these, across the ensemble of these firms, I should report the posterior mean. Okay, but I might have other objectives, and in the firm context, there's interesting classification decisions that I might be specifically interested in. In particular, I might care about which firms are discriminating at all. Okay, which firms have delta exactly equal to 0? Which firms are violating the Civil Rights Act? Which firms are not in the discrimination context? I might care about which firms are in that upper tail that seem to be driving a lot of the action in the experiment. Which firms are above the 80th percentile of the G distribution? Okay, we saw kind of a toy example of how to do that. There's various ways to approach these tail selection problems. The approach I want to kind of offer here in closing is to link this EB state of mind with the multiple testing literature, a bit like Jiaying did at the end of her part, and by noting that these sorts of decisions are closely related to multiple testing problems. So Efron in his book calls this large-scale inference, trying to do inference in this world of many estimates at the same time. And let's think about some robust empirical Bayes methods to approach this sort of multiple testing problem to decide which firms are discriminating at all. Okay, so what I'm going to do is conduct a hypothesis test for each firm, testing the null that delta F is equal to 0. Maybe I want to do a one-tailed test if I believe this result that everybody is going in one direction. I do a one-tailed test of delta F equals 0 against the alternative that it's bigger than 0. My test statistic is, of course, just going to be the z-score, p-value 1 minus phi of the z-score. And then I'm going to adopt a decision rule that says let's reject all hypotheses below some p-value threshold, p-bar. How many mistakes do I expect to make with that decision rule? Well, I think the empirical Bayes type of approach provides a natural way to think about that question. How many mistakes do I expect to make? One way of formalizing that question is to say, what fraction of the firms that I label as discriminating with this decision rule, p below p bar, are actually not discriminating? Okay, so what share of firms have delta F equals 0 among those my decision rule selects as discriminators? By Bayes' rule, I can write that as the probability of getting a p-value below p-bar, given that you're not discriminating, times the marginal for delta equals 0 over the marginal for p below p-bar. This first piece, since under the null the p-values are uniform, that's p-bar. Okay, the denominator is the marginal CDF of the p-values evaluated at p-bar. And then this first thing, the kind of prior probability of the null being true in this case, that's pi naught, we'll call it. And in the multiple testing literature, this thing has a name. This is the false discovery rate in a kind of empirical Bayes way of looking at the problem, or FDR for our decision rule. It tells me, on average, among the nulls that I select to reject, what share should I expect are actually true? All right? If I can limit my FDR to Q bar, say 5%, I should expect at most 100 Q bar percent of those I classify as discriminating to actually not be discriminating, 1 out of 20, say, if it's a 5% threshold. So let's see how we can control FDR. Okay, remember this first part is easy. That's p bar because the p-values are uniform under the null. The denominator is something I could try to estimate. That's the marginal CDF of p-values. I observe a bunch of p-values from this population, so I could estimate that somehow. Maybe the empirical share below p bar. The hard part is the pi naught. Okay, the hard part is knowing in this ensemble that I'm looking at how many of the nulls are actually true. What share of the nulls in this population are true? In this empirical Bayes way of looking at the problem, that's a feature of my G. Okay, that's a feature of the G distribution. It's the integral over G of indicator for delta exactly 0. So in G, how many deltas are exactly 0? And in general, we treat that as partially identified. It's very hard to tell the difference between a world where a bunch of firms are at exactly 0 versus just vanishingly small contact gaps that are not exactly 0. And depending on which of these deconvolution approaches I took, I may have already taken a stand on this. Actually, if I did the Efron smooth approximation, I've already imposed that pi naught hat is equal to exactly 0. It's 0. Firms discriminate at least a little bit with probability 1, so this is actually not even an interesting question in that world. So maybe I want to do something else. Okay, the most conservative thing I could do is to plug in the logical upper limit for pi naught, which is 1, which is kind of the traditional approach to this. That actually could still imply a low FDR if I have many p-values that are close to 0. Okay, if a lot of p-values are close to 0, the marginal CDF for the p-values is going to be concentrated a lot closer to 0. But if you think about it for a second, you can do better than that, okay, because it's logically inconsistent to have pi naught equal 1, but a bunch of the p-values very close to 0. Another way of saying that is we already know the mean and the variance of G are not 0 in this case, so pi naught can't be 1. Somebody has to be discriminating, and I can use that information to borrow from the ensemble and bound pi naught in a non-trivial way. The way this works, maybe I won't go through, I guess I'll go very quickly through the details. The way this works is basically at any point in the distribution of p-values, if I'm thinking about the density, the true nulls contribute height pi naught because they're uniform, and then the alternative false nulls contribute something else, F1. I don't know what that looks like exactly, the alternative distribution, but I know it's a density, so it must be positive, and therefore the height of the density at any point gives me an upper bound on pi naught, and therefore the best upper bound is the minimum density of the p-values. Okay, I expect that minimum to be achieved somewhere near 1 because if my test is worth anything, I expect the false nulls to be concentrated towards 0, and so what I'd like to do is know what is the density of the p-values at 1. Story has this proposed tail density estimator in this 2002 paper. Basically, this is saying, look at the average height of the density above some threshold lambda. There's sort of a trade-off there. You know, the higher lambda, the better bound I'm going to get, but the less data I'm using to estimate this, so the noisier is my bound. You can think about different ways to do that. Story et al. 2004 have a kind of bootstrap procedure they propose to do this. You could also use this nice paper, Armstrong 2015, to provide a non-parametric confidence interval for pi naught. If you want to be conservative, maybe take the upper limit of that or something like that. However you do it, you get your bound on pi naught, you plug that in, that gives you what's called a Q value for discrimination for this null that we're testing. The Q value is essentially the fitted FDR hat for this firm, plugging in whatever bound I chose for pi naught. You could think of that as the EB equivalent of my p-value rather than controlling the probability of type 1 error, the probability of rejecting given the null is true. I'm using Bayes' rule plus the ensemble of tests together to control the probability of the null being true given that I reject it. So to invert that expression and control the expected share of true nulls among those selected for rejection by my decision rule. And if I get a Q value of 0.05 for a particular firm, I should expect at most 5% of those I select for rejection to actually be true nulls on average, okay, in expectation. So here's what happens if we do that in this experiment. This is the distribution of p-values. You can see there's a bunch of discrimination going on. A bunch of them are near 0. The story procedure produces a lambda that's like 0.5. That gives me an estimated upper bound on pi naught of 0.39. In other words, at least 61% of the firms are discriminating against black applicants. I plug that in. I get a bunch of small Q values for a bunch of these firms. So 23 of the 108 firms in the experiment end up with Q values below 0.05. That means I should expect roughly at most one firm on that list to not be discriminating if you kind of buy the procedures that we've done to get here. And I had some other decision theory stuff at the end, but I think in the interest of leaving time for questions, I'm going to conclude right there. And thanks everyone for listening.